So the other thing that comes out of these flows and processes that generate displacements of air parcels and gravity waves is something called inversion. Obviously, it's exactly what it says. Inversion is where you have cooler, heavier air below warmer air aloft that becomes very stable. So if you're generating pollution, then it becomes harder to mix up and disperse away pollutions. There are various places where inversion is a part of the natural seasonal changes in the circulation, etc. But there are also places where urban heat island and so on can generate inversion. So one example here is that you have our normal daytime temperature profile, but come night you can produce low-level inversions where you have weak winds and wintertime nights, which allow for a lot of radiative cooling of the surface because there are no clouds, and long wave radiation can escape out of the boundary layer into space or the upper atmosphere and produce rapid cooling of the surface. In an urban environment, for example, dry land, paved lands with high albedo, for example, can create such inversions as well. You can also have a situation where you have air sinking. We'll see an example of the trade winds where descent happens and the air gets adiabatically compressed and warms up, right? We will see a little bit during the trade wind inversion. I'll explain why the descent and compression and warming doesn't increase buoyancy and allow the air to rise back. Okay, that is related to, again, radiative cooling. So these are the ways you can create inversion. You can see there is a clear inversion of temperature, cooler temperatures near the surface, and then a rapid warming of the air above, which makes the mixing much harder, especially if you have light winds. Strong winds can always mix away things, right? So here is an example of a satellite image of haze over eastern China. This has a lot to do with mixing in with the dust storms from the Gobi Desert, local pollution, local urban heat islands, and so on. And the circulation in LA can also often trap the pollution created by automobiles and other sources near the ground. The fog, smog pollution can just hang around because it cannot be mixed away into the upper atmosphere. So that's a very good example. New Delhi is very famous for its pollution in the winter months, and it is greatly compounded by the transition from the so-called Kharif season, or the monsoon harvesting season, into the Rabi season. So the farmers don't want to spend the money on a tractor to till the land and remove the crop residue left behind from the previous season's crops, Kharif crops. So they just light the crop residue and it burns freely, and that smoke can create massive air pollution problems over New Delhi, and this is a debate every year, and we are right there in October. So next month we are going to have this debate again about inversion, crop burning, and pollution loading up New Delhi. Sometimes it becomes so bad that people just move out, especially foreign companies, embassies, and so on. So it's not a good situation, right? You can also create it by situations like this, where you have prevailing winds bringing in cool marine air onto land and running into the warm air that's on land, and the cold air forces the warm air to rise on top because it's lighter. So cold air will come in. It's called a cold front when cold air mass runs into a warm air mass that's in place. So that can also create cold stable air below under the warm air above. We haven't done the subtropical high, etc. in this course yet, but you've probably seen it somewhere. So we know that the sinking or descent of the Hadley cell over the subtropical region produces descent, compression, high pressure, clear skies, no rain, etc. These are in fact the deserts of the ocean in the Pacific, Atlantic, and southern Indian Ocean. Northern Indian Ocean has the monsoonal circulation. Nonetheless, air just like air rising in the atmosphere expands and cools, air that's forced to sink obviously compresses and warms up adiabatically. But why doesn't it then become lighter and go back up? Because as it's descending and warming and compressing and warming, it's clear skies, so it's also radiating energy out to space. So there is a kind of a balance between the warming due to compression and radiative loss. Hence, this sinking becomes quite slow. It's not a very fast sinking associated with a convection, for example. Convective cell can have very fast rising motion and very fast sinking motions where ambient air can get entrained into the convection, etc. We won't go into that. So this is how it looks. You have the warm tropics here where you have rising air and huge towers of rain-bearing clouds. The rising air hits the tropopause, and you can see the wind shear causes the advection of the cool moist air and the cloud, creating what's called an anvil. We will see a little bit later on in this same chapter. And the air goes poleward, which is basically the Hadley cell that we are showing here. And here is the subtropical high that we looked at from the top in the previous picture. And obviously this is the strong descent region with a strong trade inversion. And within the flow that's coming back to supply the rising air, so you actually have air going from a cooler place to a warmer place. So obviously this is not transporting heat poleward, but we'll come back to that later on. So along the way there are these little cumulus convections which are not rain bearing. They just go above a few kilometers, and you can see that they have weaker descent as you go towards the tropics. So you have strong ascent, strong descent, and weaker descent and weaker trade inversions. So inversions are common phenomenon again. So every time you have very heavy pollution, especially during winter months, you may want to see if the region you are looking at has in fact a inversion created by any of these processes. Okay?